Hey, Dr. Fodder here. We are continuing with Chapter 2 on the chemistry of life. We are picking up on the section where we start talking about the atom, right? And the atom is going to be the smallest unit of matter that still retains the properties of an element. So in other words, if I take that hunk of graphite at the end of my pencil that is made of all carbon, right, elemental carbon, if I subdivide that graphite smaller and smaller and smaller and smaller, right, the smallest that I can go in that hunk of graphite, in that hunk of carbon, and that, piece of graphite or carbon, if it still retains the properties of self, the smallest unit, right, of matter that can still retain the properties of an element is going to be an atom. Okay, so this is a kind of fundamental threshold of matter and of chemical properties, is this idea that this is the smallest unit of matter that still retains the properties of an element. Okay, if we go smaller than that, though, right, we're going now into the land of subatomic particles. Okay, and these particles, they are what make up an atom. But why they're subatomic, why they're, below this threshold of an atom, is that if you go smaller than an atom, right, although an atom will still retain the properties of that element, these subatomic particles will not. Okay, and in fact, these subatomic particles, when they come together in an atom, there's a kind of, they are in different locations in the atom, they have different properties, and so, when they come together in an atom, they'll kind of come together as a group to give that particular elemental atom, like, its properties. But individually, these subatomic particles, they make up that atom, and they're going to behave a little bit differently. There are three types. We have protons, neutrons, and electrons. And one of the most important ways that we group these subatomic particles is by charge. So neutrons have no electrical charge, protons have a positive charge, and electrons have a negative charge. Okay, where they are located, if you could think about, like, let me just find a picture. This is a good picture. Okay, so generally speaking, the nucleus is the dense and has a lot of weight center part of the atom. And that center part of the atom, the nucleus, it contains protons, which are positively charged, and neutrons, which are neutrally charged or have no charge. So great, that's the nucleus, and those are two out of the three subatomic particles. Our last subatomic particle is going to be the electron, and electrons are going to live outside of the nucleus in things called energy shells, or if you've taken, introductory chemistry or quantum chemistry before, they're going to be living in a place called orbitals. Electrons, of course, they have that negative charge. The other thing that I need to let you guys know about is that in terms of relative mass, protons and neutrons are much, 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 much heavier, like at least 2,000 times heavier than an electron. So really the matter that makes up an atom is going to be those protons and neutrons in the nucleus. Okay. By contrast, the electrons, when they're zipping around outside in their energy shells or in their orbitals, they're small, they're light, they're fast. You can either know where they are or where they're going, but you can't know both at the same time. Actually, that's a really super interesting thing about electrons. The thing about electrons, though, is that really they are responsible for the chemical behavior of an atom. Okay, because these electrons, how they behave is they'll do one of these two things. They're either going to be shared when atoms make bonds, right, and when atoms come together to make compounds, or electrons will be transferred. They'll be given away or they'll be taken. Okay, so when they have these behaviors, either being shared by two atoms in a bond or being transferred, right, between two atoms in a bond, it's really these electrons that are going to determine the bonding behavior of atoms when atoms make compounds. Okay, so that's kind of just a heads up. These three different subatomic particles, they have different charges, they have different locations, they have different masses, and they also contribute different functions in terms of atomic behavior. Okay, so how do we as scientists talk about these subatomic particles? How do we as scientists talk about these atoms and these elements? And, what is the way that we communicate with one another about these things? we have these quantities, okay? Atomic number and atomic mass. And an element's atomic number is the number of protons in its nucleus. So I'm going to go back one slide. So if you take a look at the number of protons in an atom's nucleus, that number of protons is going to be that atomic number of that element. And the interesting thing about that is that the atomic number for an element is going to be really how we identify that element. So atomic number 6, if something has 6 protons in its nucleus, by definition, that atom is going to be the element of carbon. By definition, if there are going to be 15 protons in an atom's nucleus and the atomic number is 15, we know by definition that atom is a phosphorus atom, and it's the element of phosphorus. So again, the atomic number, it's the number of protons in the nucleus, and the number of protons, it's that how that works is that it identifies what element that atom belongs to. The second way that we talk about chemistry and atoms and the subatomic particles is an element's mass number. Now, this mass number is the sum of protons plus neutrons in the nucleus. So I'm going to go back one slide again. Okay. Now, for mass number, I'm not going to just think protons. I'm going to think protons plus the neutrons that are available, okay, in that nucleus for that atom. And what that does, that mass number, that tells us the isotope of that atom, or the isotope of that element, okay? And isotopes, we have stable and unstable isotopes of different elements. Some isotopes are stable, and some isotopes are unstable. And when we say that they're unstable, that means that they have a tendency to emit energy or subatomic particles, and they will be radioactive as they give off those energy and particles. So when we talk about the mass number of an element, we talk about its isotope, usually whether or not it's going to be a stable and non-radioactive isotope, or if it's going to be an unstable radioactive isotope that gives off particles and energy, okay? And atomic mass, that's the atom's total mass, and that's approximated by the mass number. It's roughly equivalent to the mass number, right? Because most of the mass of an atom is going to be the protons and the neutrons, okay? And the other reason the atomic mass is approximately the mass number, well, that's going to be because there's different, it's kind of an average of all of the different isotopes. It's a weighted average of the different isotopes of that element. And so that's how we get atomic mass. It's approximated by the mass number. It's a weighted average of the different masses of the different isotopes of that element. I want to see if here. This is a good, I'm sorry I went ahead so far, but I just wanted to kind of show you what this looks like. Whenever we have the periodic table and we're communicating with other scientists about these atoms and these elements, we can find these numbers, the atomic number, the atomic mass, and even the element symbol on that periodic table. So when you're looking at the periodic table, and you're kind of looking at one of these squares, these rectangles for each of the elements, right? The information that we just talked about, atomic number, atomic mass, is written on the periodic table for us to be able to look at. So, for example, if I'm looking at the periodic table, this is the element symbol, right? This element symbol, He, stands for helium. The number on top, right? This is usually a prominently written number. This is it may be like bolded, it may be in red, it may be written bigger than the other number on that particular periodic table rectangle. This is the atomic number, and again, this is the number of protons in that atom, and this number identifies specifically the element that atom belongs to. And then usually there's a number at the bottom with some decimals. It's usually written smaller or less prominently. Maybe it's not bolded. Maybe it's only in black and it's not red. It's the less prominent of the two numbers on that square or the rectangle on the periodic table. This is the atomic mass. And again, this is approximately the number of protons plus neutrons in that atom. Okay, so if you're taking a look for where this information is, you can find it in the periodic table. And therefore, you can use that information in the periodic table to kind of have a picture for yourself of what this atom looks like. All right, I'm going to go back to that slide. Sorry about that. Okay, so in terms of the chemical properties of an atom, Okay, again, an isotope is determined by the mass number, so that really the number of neutrons plus protons that are in the nucleus. Isotopes are two atoms of an element that differ in the number of neutrons, and we usually name an isotope by the mass number that it is. So like carbon-12 versus carbon-13, these would be two isotopes of carbon. One would have 6 protons and 6 neutrons, that would be carbon-12. Carbon-13 would have 6 protons plus 7 neutrons. So again, those two isotopes, they would be two atoms of an element that differ in the number of neutrons. In the case of carbon-12 and carbon-13, carbon-12 would have 6 neutrons and carbon-13 would have 7 neutrons. Radioactive isotopes, the ones that are unstable, they decay spontaneously and they give off particles and energy. And they do that because really that atom is trying to get to a more stable state, and in order to do that it has to give off particles and energy to get to that more stable state. It sounds kind of scary because those energy and the particles can do damage to living tissue around it. However, because we know about this, right, first of all, we can take precautions to shield ourselves from that emitted particles and energy so that our tissue isn't damaged. And the second thing is we can actually, if we anticipate that radioactive isotopes give off particles and energy, we can actually use radioactive isotopes for scientific purposes. So, for example, radioactive tracers, these are isotopes that are used as diagnostic tools in medicine, right? Basically, you take like a molecule, like sugar, and it turns out that tumors are really, really, really good at metabolizing sugar, because tumors, their cells are dividing all the time. It's a work-intensive process to do cell division, and so they need a lot of sugar. They need a lot of energy in order to keep dividing, in order to keep that tumor growing. Because of that, those tumors will kind of be hotspots, or places where glucose is going to, or sugar is going to concentrate right in our body. Now, because we know this, right, and because we're interested in finding out where those tumors are in our body, something that we have done as scientists is we have attached radioactive labels to sugar, right? We've put radioactive labels on glucose, right? We can put that into a patient, and because tumors have will concentrate glucose in themselves because they need that glucose in order to keep dividing and in order for that tumor to keep growing, right? What do you think is going to happen when that radioactive glucose finds the tumor, and that tumor keeps on taking in that radioactive glucose so it can keep on dividing? Well, take a look, right? That tumor then can be labeled with that radioactive glucose because that's going to be where that radioactive glucose is concentrated in the body, right? And so now we've taken this phenomenon of radioactivity and, with a little bit of thought and creativity, we've turned it into a tool for being able to do something positive for patients. In this case, because that radioactive glucose concentrates in the tumor, and because we can have a scanner of some kind that detects where in the body the radioactive glucose is concentrated, we can now more precisely figure out, right, through FDG PET scanning, where that radioactive glucose and where that tumor are. And in this case, in this figure, it's in cancerous throat tissue. So that's one application of isotopes. And again, an isotope is just an element, a version of an element with a different number of neutrons. In some cases, it's going to be stable and it's not going to emit energy or particles. But in the case where that isotope is unstable, it is going to emit energy and particles. But we can use that emission of energy for scientific purposes. The other application that your book has for radioactive isotopes is radiometric dating. So if you've taken a geology class, you probably have heard of carbon dating before, where you can look at how old something is based on the amount of radioactive carbon-13 that's left behind in that object. So this is just a second application of radioactivity and of isotopes. Again, that type of element, that version of that element with a different number of neutrons that makes it unstable. Okay, so if protons identify an element, if neutrons identify the isotope, right, we're going to finish this part of the chapter by talking about electrons. And electrons, why I love electrons and why electrons are super important is because, again, they determine bonding behavior. Okay, so let's talk a little bit about electrons and kind of how they live around an atom. Take a look at this. Basically, electrons are going to live in these different energy shells around an atom, around an atom's nucleus, excuse me. And the way that it works is that the closer to the nucleus of an atom you are, the lower in energy that energy shell is, and the farther away that that energy shell is around the nucleus of an atom, the higher energy that that energy shell is. And so basically electrons, when they're zipping around the nucleus, depending on the amount of energy they have, they're going to be living in different orbitals. If they have low energy, they're going to be living in the first energy shell. If they have higher energy, they're going to be living like in outer energy shells. Okay, so that's kind of where electrons live in an atom around the nucleus. Okay. And really how these energy shells fill with electrons is like this, right? And this is why I love the periodic table so much, is because the periodic table not only has all of the information about atomic number, atomic mass, and the element symbol, but it also, in addition to giving us that information about protons and neutrons, it also gives us information about electrons, where they live, and how many are in each energy shell. Because the shape of the periodic table, right, gives us the information about how many energy shells an atom has, and it also has information about how many electrons are in each energy shell. So the way the periodic table works is whatever row that you're on, if you're an atom, that's how many energy shells that you have. So if I am hydrogen and I'm on the first row of the periodic table, that means I have only one energy shell. If I'm sulfur and I live on the third row of the periodic table, right, that implies that I have 3 energy shells. And if I'm carbon and I am on the second row of the periodic table, that tells me that I have 2 energy shells. So that's the first thing that I know about electrons, is that how many energy shells that I have around the nucleus of an atom is determined by what row of the periodic table that I'm on. Okay. Second thing is, okay, when I fill up my energy shells with electrons, what I'm going to do is I'm going to count from left to right, how many columns that I've gone across on my periodic table. And by having that count, I know how many electrons I'm going to put into that energy shell. So take a look at this, right? Hydrogen's in my first column on the left, so I'm going to put 1 electron in that first energy shell. Helium is 1, 2, right? There's a bunch that I skipped, but the first row is kind of funny. But helium is in my 1, 2 second column on this first row, on this weird first row. So that means I'm going to put 2 electrons in that first energy shell. And because I only have 2 columns on this first row, that means that that energy shell is going to be full with 2 electrons, right? Pretty cool. When I go to my second energy shell, and I'm lithium, and I'm in my first column, that means I'm going to have 1 electron in my 1, 2 second energy shell. I'm still going to keep those 2 electrons in the first energy shell from that first row, right? Because that's the first row. I'm going to build and add on that first row, and I'm going to build and add on those electrons. So lithium, second row, second energy shell. It's in the first left column, so I'm going to put 1 electron. Beryllium is going to come next, so 1, 2. That means I'm going to put a second electron. Boron comes next, 1, 2, 3. That means I'm going to have 3 electrons. And you can keep on doing this. As you move from left to right, as you keep on moving in these columns, you're just going to keep adding these electrons to that outer energy shell, all the way until you get to neon, which is 1, 2, 3, 4, 5, 6, 7, 8, right? 8 columns over. So how many electrons do you think that that second energy shell has? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. Right? Oh my gosh, I love the periodic table so much. Okay, we're going to do the third energy shell, but you can imagine it's going to be the same thing. So take a look. Now I'm on the third row. I have 1, 2, 3 energy shells. From sodium to argon, take a look. 1, sodium. 1, 2, magnesium. Aluminum, 1, 2, 3. Aluminum is in the third column, right? So that means it has 3 electrons, and that's going to keep on going until, of course, we get to argon, which is in the 1, 2, 3, 4, 5, 6, 7, 8th column. So you can guess it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its third energy shell, right? And that's how we build the periodic table. And that's how we figure out how many electrons are in these energy shells and how the electrons are arranged, right? So if you just have a periodic table, and you remember those rules of the row is the number of shells and the columns is the number of electrons in that shell, right? We can draw a picture of any atom, right, on that periodic table. Now, for the sake of this class, I'm only going to stick to these first three rows or 3 energy shells. I'm also going to omit all of those transition metals that are kind of in the long skinny part in the middle of the periodic table. Okay, so we're only going to be doing the metals on the first 2 left columns, and we're going to be doing the non-metals, right? The stuff in the 1, 2, 3, 4, 5, 6 most right columns. We're going to be omitting those transition metals for the sake of this class, okay? But here's the thing, right? This is actually going to be one of our first short answer questions, is how do you draw a picture of an atom? How do you draw an electron distribution diagram? Okay, so my suggestion is please take a look at the worksheet in your assignments and I think it's assignments and practice folder or something like that in your week 2 course folder. There should be like a practice worksheet there. Go ahead and get some practice in drawing those electron distribution diagrams for those different atoms. Okay, what you can do is, close your PowerPoint, get a copy of the periodic table that doesn't have the pictures of the atoms, and then just using the information about where it is located on the periodic table and the information of the atomic number, the atomic mass, and the element symbol, go ahead and try to draw an electron distribution diagram that shows the number of protons, the number of neutrons, and the number of electrons for an atom. Okay. Take a look at that practice worksheet. I'll try to put the answers later this week. Thanks for your attention. We'll go on to chemical bonding in the next video. Thanks, bye.